So I should be able to see that. Okay, I'll start record. Yeah. Okay. Yeah. Okay. So before we begin, okay. So just a recap from yesterday. So this section is on STP operations. Right. So we've learned so far the first step to create a loop-free topology. Yeah, because we want redundancy, right? But redundancy allows uh, perhaps because of broadcast, yeah, um, broadcast packets like or broadcast frames like ARP, yeah, then it can bring down a network because of broadcast storm, right? Okay, so we need a way to provide redundancy while at the same time we want to prohibit the formation of a loop. So the solution is basically pick the best path, okay, then the alternate path or paths, maybe more than one, we disable. All right. So now what we're going to go through is actually the basis of STA, the spanning tree algorithm implemented in a protocol. So we will follow step by step what the switches will do in order to well, first of all, um, to elect the root bridge, right? And then after that is successful, elect the root ports, and then elect the designated ports, and then elect alternate block ports. Okay, once that done, then the STP um, is complete. Yeah, right. So why you can see all the steps are they are all four and they are all elect because there are situation when everything is equal. When I say everything is the the information, the BID inside the BBDU, right, happens to be all equal. So we know already for the root bridge, the BID, the information that breaks the tie is the value of the MAC address, right? So whichever switch has the lower value MAC address will win, and that switch becomes the root bridge. Of course, we look at from the higher one first, how higher ID, like bridge priority, for example. When everything is equal, then we use the MAC address as a tiebreaker, right? So we learned already how to elect the root bridge. Okay, each of the switches, they are sending each other their own uh, BPDU, right? So this BPDU is sent between switches. So each of the switch by default elect themselves to be root bridge until they they receive other BPDUs from other switches. Okay, they will start comparing. So they will start comparing between the received BPDUs and the switch owns BPDU, right? In fact, the detail is the BID. Okay, all the BID is being compared as the switch received them. When the switch detect that its own BID is higher, means it lost the election. So that switch will change its state from being the root bridge to normal switch, right? So and then of course whoever of the switch discovered that none of the other BIDs from the other switches are lower than its own BID, then it will remain as the root bridge. In this way, it settles down. It settles down in the sense that once all the BPDUs have been received by all the switches and they made a comparison, you will eventually be left with one of the switch will be the root bridge. Okay, so this is how the election happens, right? In fact, this you can say this is implicit, it's not explicit, because none of the switch actually tells the other switch that, hey, you are or IM, you know, is understood from the comparison they themselves doing, right? As I said before, each switch will compare all the other BIDs with its own BID, right? If we discovered that another switch BID is lower than its own BID, it will relinquish the root bridge role. The opposite is if the switch receive, because by default it elects itself as a root bridge. When it receives a BID that's lower than itself, then it will relinquish. If not, none of the BID that is received from other switches are lower than its BID, then it will remain as a root bridge. So you can see there, right? After the switches all settle down, there will be one switch that is operating as a root bridge. Okay, so we got that already, right? So what we consider, compare is the bridge priority, and then uh, you can see. Let me just move forward. Let's say if there is right here, right? So bridge priority is detected first. Now bridge priority will by default has the same value. Okay, it's a default value from the Cisco switch. For the Cisco switch given by Cisco, which is 32768. Right? If this one all equal, then you start looking at the switch will start looking at the second info, which is the extended system ID. In fact, the system ID is basically taking the priority and just adding the VLAN ID. All right. And in the sense that if all the switches in operation belongs to the same VLAN, right? So the VLAN will be the same because you add up to uh, the priority, then they all will be equal again, right? So when the second comparison still cannot break the tie, then we go to the last one, and this definitely will break the tie because MAC address is definitely unique, right? Unique, that means they will never be the same. So you will always find which among the MAC addresses of the switches will be the lowest, and that switch will win, right? So if you are a system administrator and you want to influence this election, what you can do is identify the switch that you want to be the root bridge and lower the bridge priority by increment of 4096, right? And definitely, since the rest of the switches have a default of 32768, the switch that you want to win, you just set the priority value lower, then that switch will be the root bridge. Okay, right. So we've done this exercise yesterday, right? So we also done this one, electing the root bridge, right? And then we look at the impact of the default bridge IDs, right? If they are the same and then the priority is the same and the extended ID is the same, then we look at MAC addresses, which is the lower MAC address will win, right? Which has the lower MAC address will win. So this is the info that will break the tie. Okay, so called will break the tie, lah, right? Right. So we've done that, and then this determining the root path cost is the cost here indicates the best path, right? For the other switch to go to the root bridge, right? So there is a calculation involved, okay, very simple calculation, and also the default values that Cisco follows is the IEEE, as you can see in the table, right? You can see in the table here, right? So we are going to look at this one, the Stp cost, right? So Stp cost, well, to actually assign a value to link speed. The link speed, basically the port is capable, what kind of speed, right? Of course, we will assume here that the cable that you connect is suitable cable. It means it's capable to achieve the the speed that the port is allowed to have. So we have 4 variation of link speed here. Fastest being 10 gigabits per second and the slowest being 10 megabits per second. In most general cases, the switch will have this speed 100 megabits per second and 1 gigabits per second, right? So through the assignment of a value, there's a standard way to calculate the root path. Okay, so the segment or the link, right, that which can carry the port speed. Okay, let's say 1 gigabits per second will be assigned a value of 4, right? And to calculate, okay, to calculate the path is from the switch in concern until you reach the root bridge. So there might be a direct connection, right? Or it might be over 1 or 2 or more switches. So the path cost is just a total of the values you assign depending on the link speed at each segment, right? Okay, so this is how we calculate lah. And of course, the switch knows its own speed, so it knows how to add on to that value, right? Now, auto switch, the cost is configurable, right? The ability to configure individual port costs give the admin flexibility. So that means this cost, although it's the default, and the default follows the IEEE standard, yeah. But as an admin, you have the choice to come into the switch and manipulate that value, right? So basically, you can sort of bias certain value to so that the calculation with the path cost will favor, okay, the path that the admin, the network administrator wants to have, right? Okay, this is a way for you to influence the selection of the calculation of the path cost, right? But in most time, of course, we will just take the default. Why? Because we want the benefit of knowing that it will automatically pick the best path for us, because the best path here is the fastest way to reach the root bridge. Okay, it's just a extra thing that allows configuration, because there might be some situation where the network administrator prefers certain configuration. Okay, okay, so this is the part. That's the part where we end up yesterday. So we proceed with that, knowing how to calculate the path cost. Yeah, okay, is important for us so that we know how to elect the root ports. Okay, the root port usually indicates that that port leads to the root bridge. Okay. Now, before we continue here, I just want to say that, let's say in this example, switch 1 is the root bridge. So for the S1, there is no root port there. Okay. All the ports emanating, excuse me, from the root bridge is called designated port. Okay, for switch 1. Okay, for switch 1, since switch 1 is the root bridge, none of the ports on the switch 1 will be root port. Okay, they will be indicated as designated ports. All right. Okay, so once we get that, so we have to look at the other switches. So in our consideration here, we have S3 and S2, right? So every now, because S1 cannot have root bridge, so S3 and S2, each of them must have root port. Okay, since they are not root bridge, they can have root port. So each one of them will have a root port. Okay, so the root port, okay, usually is the port closest to the root bridge. When you say closest, okay, not necessarily physical distance. It's more towards the path calculation just now, the path cost. Which one has the lowest path cost? Okay. But of course, if you have S3 and S2 in this diagram here, they are directly connected to the switch, right? The port F1 on S3 and F1 on S2, okay, they are directly connected to the root bridge. Then you know they are, for each of the switch, that port is the root port. There's no other port that can, that basically has a better path cost, right? As you can see, F6, F8, F11 doesn't even go to the root bridge. So, and F2 goes to another switch rather than the root bridge. So we know that for S2, F1 is the root port because of that, right? There's not any port on the switch 2 that has a better path cost compared to F1. So similarly at S3, when we look at it, we consider two ports on S3, F1, F2. Again, immediately we can see F1 has a direct link to S1. S3 has the port F1 on S3 has a direct link to port F2 on S1. Therefore, F1 on S3 is also a root port. So S3's root port is F1. S2's root port is F1 as well, but its own S1. Right? Okay, so far okay?
Yeah, okay.
Okay.
Do we need to do the math when we answer?
The math. Maybe you have to, if you have to calculate the path cost, that's the only math you do.
Do we have to show it?
Just, yeah, something like this. Path 1, path 2, only if the question asks
Or
for it. Right? If they say justify why you select this, then your part of your justification is actually to show that the path costs are, then you have to show how come this path is better than this path. So the only way you can show it is to provide the comparison of the path costs, right? So the path cost, once you show the comparison of path cost, to show that you're not simply picking it up of thin air, you show the calculation of the path cost. And the path cost, if you notice, will be based on this, yeah, right? So you have sometimes this table is not given, right, in the question. So if you're face-to-face exam, probably you have to memorize this. If your open book exam, so you can refer to this. Okay, but most of the time in the diagram, it will be between the 1 gigabits per second and 100 megabits per second. So the two numbers that you have to think about or remember is the path cost of 4 and 19. Okay, most switch don't have 10 megabits per second anymore. Actually, 10 megabits per second is for very old switch or hubs, and hub doesn't come into this consideration. Hubs has no idea about any of this because hub is on layer 1. So and in fact 10 megabits per second speed is for those legacy bus network. I seldom see, or I don't see any more switches with 10 megabits per second. So usually it's a, so that means during the test, what kind of question you will see if they ask you path cost is the one with the 1 gigabit per second or 100 megabits per second, right? 10 gigabits per second is also not very, how to say, common yet, right? Or maybe because I'm not privy to large enterprises network. Maybe they can afford, right? They can afford the switches with 10 gigabits per second speed and cabling that is can go maybe I'm not sure Cat 6E can or not, right? Or STP needs to 10 gigabits per second, you need a better cable, right? So most of the examples will be these two, right? Right, so where was I? Oh yeah, overall cost is known as the internal root path cost. So that means if you're like from S2 and you want to calculate the path cost for F2 on S2, then this path 2, you see that there are two arrows. Okay, this combination of these two, right, is based on a calculation. If you see here, fast Ethernet is 100 megabits per second, so it's 19. So 19 plus 19 is about 38, is it? 38. So this path cost is 38, the path 2. Whereas the trunk one, okay, path 1 is only half of that, 19. Right? Okay. So this is what we this is our method to calculate the root path cost. Right? Yeah. So, and it's actually described here. The internal root path cost is equal to the sum. You add. As long as you have another segment, 1, 2, and if you have more than, here we only have 2 for path 2. So, but the internal root path cost is combine these two path 2, both the path 2 segment right? Right, so path with the lowest cost becomes preferred and all other redundant paths are blocked. So that's the idea, because lowest cost means lower latency. Okay, the bandwidth will be the same. Okay, bandwidth will be the same, but the extra segment and extra switch in the middle introduce latency. Okay, so the straight path, for example, the path 1 has lower latency compared to latency here, delay compared to path 2, right? Right, so that's why path with the lowest cost becomes preferred, and all other alternate or redundant path will be blocked by the STP, right? Okay. Right, so path 1 has an overall lower overall path cost to the root bridge, so it's the preferred path. So F1 becomes the root port on S2. Okay. In fact, each switch that's directly connected to the root bridge, usually that port that is linked to the root bridge will be root port. Okay, but if you have more than these two, means you have a third one. Let's say you have the third one which is not directly linked to root bridge, then the calculation this one is straightforward, basically S3 and S2, because they're directly linked. So you straight away know that one is root port. But if you have another switch, okay, switch 4, 5 or something here connected to S3 and S2, which is not directly connected to S1, then this is the calculation that you have to do, the overall path cost. Okay, so the one with the lower path cost will be the root bridge for the switch. Okay, so we're not talking about this and this. We're talking individual switch. So let's search for switch 2. You got 2 ports leading to root bridge. Which of the ports is the root port? F1, because F1 wins based on lower path cost, only 19. Only 19. Whereas here is 19. Here also 19. So if you take the F2, it's 38. Go here first and then go here 38. Here, F1 wins because it's only 19. 19 is lower than 38. Okay, got it there? So the F1 is the root port for switch 2. Now, we dealt with S2. Now look at S3. S3 also have F1, F2. Okay, so for S3, the path is F2 is going to switch 2 first, and then go to S1. So that's again, that is 38. Okay. The other path between S3 and S1 is a direct path, only 19. So it wins by having the lower path cost. So for S3, F1 is the root port. Okay. So all this words here means that summarize it for you guys. Is that okay?
Okay.
Okay.
Yeah. All right. So
If-
that's
if
number
it's-
one covered.
If it's F,
Sorry?
if it's F0, if it's F fast internet, it's 19. Then if it's G, it's different.
Yeah. If it's G, different matter, right? Remember, look at this. G is only, let's say, even if 10 gigs or 1 gig. So 4, even if the this one has two segments to go by, but it's 4 plus 4 is only 8, you know. That's
Which
a
one?
big difference.
Which one is then? There's only G and F.
Yes, there's only G and F, but there's two types of G, 10 gigabits and 1 gigabits. But you, like I say, usually in our example or in our test, we only focus on 1 gigabits per second, 100 megabits per second.
Okay.
In fact, the switch that we are using, right, packet tracer, it's basically a switch that have this by default only have fast Ethernet and gigabit. Gigabit is 1 gigabit per second, right? But imagine, let's say, Kevin raised a good scenario. What if the S2 instead of F2 it has G1? So G1, this one is G1. This one could be G1, could be fast Ethernet as well. Oh, sorry, gigabit also. So if this is gigabit, it becomes 4. Sorry, 4. Right? But still, if this is 19 plus 4, still this one wins. But if this is both 4, gigabit this direction, gigabit this direction, that's 4 plus 4 is 8. 8 is lower than 19. Suddenly, the root port is no longer this. Now the shorter is this. This is gigabit, this is gigabit. Can you see that? Due to this table. Gigabit 4, right? So if this is gigabit, this is gigabit, this is 4. So if this is gigabit, this is 4, right? Even though when you look at the diagram, you have to pass by S3, but 4 plus 4, the total path cost is 8. Then when we compare against this fast Ethernet, although this is a direct link, it's lower than 19. And so in that case, the other port, F2 will win. Sorry, not F2 anymore, right? Gigabit 1 lah. Imagine, because it's gigabit. But in our example here, they are all fast Ethernet. Therefore, 19 of course slow. Here 19 means 38. The whole thing is 38. Here only 19. So 19 wins over 38. So that's why this is root bridge, right? This is root bridge. And same here, root bridge also. Is that okay?
Okay.
Right. Now, we've done root bridge, root port. Okay. So once we know root port, we're going to look at designated port. Right. So it says here, every segment between two switches will have one designated port. One designated port. Meaning to say, if the other one is, you already know is not designated, then the other end of the link on the other switch will be designated, right? If this end is not designated, then the other end of the link will be designated port. That's what it means, yeah. Every segment between two switches will have one designated port. Now, your job is to figure out which port between the two switches, okay, the link between the two switches, which port is the designated port. Now, since we already know about the root port just now, right? Okay, so let's have a look at this. It says designated port is a port on the segment that has the internal root path cost to the root bridge. In other words, the designated port has the best path to receive traffic leading to the root bridge. Receive, right? Receive to the root bridge. So on S3, okay, let's look at S3 first. It says leading to the root bridge is this way. Correct?
Okay.
Okay, I need your response. Correct? Correct, yeah? So if we are looking at S3, traffic leading to the root bridge means, okay, like this lah, going to the root bridge, right? Correct or not?
Yeah.
Yeah? Yeah. So it says receiving traffic means this one, is it receiving?
Yeah.
Forwarding, right? Forwarding traffic, right? Correct or not? Because you can see the arrow is going from S3 to S1. So F1 on S3 is receive or forwarding?
S3 will be forwarding.
Forwarding, right? Because
yeah.
it's going towards S1. So the port here is forwarding traffic out of the switch into the link to go to the root bridge, because we know here is the root bridge. So which port is the receiving port? This one, right? Because where is the traffic coming? If the traffic wants to go to root bridge, here, right? It's going inside. It's ingress, right? Going inside S3 to be forwarded to the root bridge. So, in other words, look at the sentence. In other words, the designated port has the best path to receive traffic leading to the bridge. Now, best path means if you have multiple paths, but we only have one path, right? So this is our best path, and it's receiving traffic, and this traffic is going to be forwarded towards the root bridge, right? So far so good. Yeah. So our candidate designated port on S3 is that. Now, how about S2? Forwarding traffic is this, leading towards root bridge, right? So receiving for S2, okay? Now we don't consider the edges first, right? It's from here. So our receiving port is F2. So let me just clear up. This is our candidate, first candidate. This is our second candidate. Right? For switch 2, this is the candidate switch designated port. S3, this is the candidate designated port. Now, why I want to say this is the candidate and this is candidate? Because, again, look at this. Every segment between two switches will have one designated port, but here we have two. Cannot be two, man. We just have one designated port only, isn't it? Okay, so one of these must go, right? So let's continue. What is not a root port or designated port becomes an alternate or block port. Now, what later when we figure out whether it's this one or this one is the designated port, once we figure out that, the other port becomes alternate / block port, right? So, okay, we don't know yet which one. Let's follow again. If all ports on the root bridge, which is this one, this is a root bridge, all ports are by default designated port. Okay, this one no need to figure out the root bridge. Okay, the root bridge, all its ports are designated port. Designated port is never blocked, never blocked. Okay, so basically in this segment trunk 2, right, we just want to figure out which port we want to block. Okay, the port that is designated is not blocked. Okay, that means it's if you open up the block port, straight away the traffic from the designated port can receive. Okay, can receive and forward, right? Okay, so okay, continue. If one end of a segment port is a root port, the other end is a designated port. So just now we looking at root port in a different way. We say which one is the forwarding one is receiving is designated, forwarding is root port. But we also have another way to look at it. This one, if one end of a segment is a root port, the other end is a designated, right? So if this designated root bridge has designated port, means the other end should be a root port. Okay, right? So correct lah. These two correct root port, designated port, right? And all ports attached to end devices, means it is F11, F18, F6, will be designated port, not block. Right? So on segments between two switches, S3 and S2 are candidate, where neither of the switch is the root bridge. They are both not root bridge. This is the root bridge. The port on the switch with the least cost path to the root bridge is a designated port. Right? So how do we break the tie? That means the port with the least cost path. Now here, when we look at the least cost path, we use a table earlier, but here is 19. Here is 19. Right? So they are tied. So what do we do when we reach this decision? Right? Now, not indicated in this example, but we have something called, let me just share something. I was trying to find information for it. Maybe you can find information on the NetAcad, but this one is quite it's faster for me just to show you. All right, so I want to show this part. Let me see first. Is it this one? Hang on. So not this one. So right. Can you see this? We have
Yes.
additional, yeah, we have additional identifier for each of the switch interface, which is known as the port ID, right? Port ID. And port ID is composed of two info, which is port priority and port index, right? When this port ID, when there is what do you say, when we have tie, it will come down to port ID. Okay, the comparison will be done on port ID. So on this, on the on the slide it's not very clear because the port ID is not shown, right? Port ID is not shown in the diagram. So we just on the slide itself, we just assume that the winning port has a selected port ID, a lower port ID, right? The winning port ID. Because if the path cost is the same, right, then it's tied. So to break the tie, we'll have to look at the port ID, right? Let me just quickly search whether the port ID is available in the yeah. You can see another example here, right? But we are going to look at this later. This is later in the slides. But you can see here, right? If there's a tie with the path cost, because when you look at the slide number, the slide or the elect designated ports, you can see that both are 19. Okay, the path cost is 19. So it's tied. So we have to break the tie. So for Cisco, the tiebreaker is the port ID, and the info I showed just earlier is the port ID info. Okay, every port on the switch will have this port ID. All right, and so that's the tiebreaker. Okay, let's see. Let's go back to our slide just to elaborate on what I mean. Okay, so you can see this is the part where, for me, it's not very clear on the slide now, right? Because it says here segments between two switch. This one lah, right? This is segment between two switch, right? Where neither of the switch is the broad bridge, the port on the switch with the least cost path, but we both path has 19, so it's tied, right? So now after that, it will tiebreaker is the port ID, right? Now happens to be in this example port F2 on S2 switch 2, port F2 on switch 2 is the designated port, right? Okay, so there's something there's an extra info there missing. How this port becomes designated port, because we saw in terms of the path cost is both 19, right? So it's tiebreaker is supposed to be port ID. Okay, so there's information here. This port, okay, this port and this port, okay, their port ID will be compared, and the port with the lower port ID wins. Okay, that's the part that I was explaining away from the slides, right? Now, what we can encounter that later with the same diagram I shown you earlier. Now, okay, so let's say we already compared the port ID, or yeah, so this one wins. Okay, so this port is the designated port. Remember, in a link, one port is designated, right? And the other port will be either root port or alternate port, right? So this is a receiving port, so it cannot be root port. So this is alternate port. If this port is not receiving port towards the root bridge, then it is the designated port. But if the other link is already a designated port, that's the port that is selected as designated port because it has lower port ID, then automatically on the other end of the link, that port becomes alternate port. Okay, so that's why S3 is having alternate port, right? So is that okay?
Okay.
Huh?
Okay.
So alternate port will be the port that is blocked. Okay, means no
Is it
traffic.
possible to have more than two alternate block
Yes,
and two
if
block?
you have another, if your topology like this.
If there's a third one, then
Yes, like
there will
this,
be two
yeah,
blocks.
like that, right? And still, this one wins. If this one still wins, then this one is also blocked.
Okay.
As long as there's a possibility to create a loop, right? Then that will the that potential to be loop will be blocked lah, right? Yes, it can be more than one alternate port. It depends on the topology lah. This is the simplest topology we can create to show the block or alternate port. All right. Okay. So right. So the block or alternate or block port is the one that is going to be blocked, right? Block. So designated port remains open, but there's no way it can forward because the other port is non-functioning. It's blocked. Okay, blocked through the what lah? Through the Stp configuration lah, right? Okay. Right. So this number 4 is that's it lah. How to get the alternate port. Get the designated port. If the other port is not root, then it should be alternate port. All right. Right. So electing a root port from multiple equal cost path. When a switch has a multiple equal path to the root bridge, the switch will determine a port using the following criteria. This is the one that is missing earlier on. And there was no example to show you the winning port because the port ID was not given. Probably have a look into the NetAcad notes online. Maybe they have a more detailed example. Okay, but we look at the lowest sender ID first. Maybe that's why. Let me see. Maybe it was not needed because the low ID is this one. Yes, low ID is this one. It did not need to go to port ID, I think. Huh? Yes, yes. Okay, port priority, port ID. I was showing you the port priority, port ID. Yeah? I didn't look at the BID. Okay, so I'll show you again. Oh, this one. This one. So I was showing you port priority and port ID, port ID, port priority and port index, right? Okay, so I was concerned why it was not shown. So why it was not shown, I believe, is because there's no need to. But I think you should still need to know it lah, because it is actually important to know, right? So this is what I mean lah. So here it says to you lowest sender by ID, lowest sender port priority, lowest sender port ID. So yeah, so you can see that the lower priority is lowest sender. Here, right? So this is receiver, right? For S3, this is receiver, so sender is this. For S2, this is receiver, sender is this, right? So lower sender, this is the winning one. Lower sender, PID. From the BID, it's already win, so there's no need to check the other two, port priority and port ID. Okay, that's why we didn't need to go down to port ID. And that's why the example here also did not show port ID as the as in the diagram. I mean, we don't have to go to port ID. We just look at the BID. BID, remember, to look at the priority, extended ID, and finally the MAC address. Okay. So far, so far, okay.
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 All right. Right. So
Is it in the priority? The three things.
sorry, this
Is
one.
it in order of priority they check?
Yeah, yeah. First check this first, and then this, and then this.
Okay.
Right. Okay. Oh, right. Just go. All right. So this example highlights this point. Okay. So here we can see that example. All right. S1 is the root bridge. So as usual, we do one by one, right? Elect the root bridge. So root bridge is elected. I think because of this, right? You can see there the VID is low compared to the rest. The rest the same, but I think this was set by the network administrator. So the BID is lower. So this one becomes the root bridge, right? So remember, all the ports on the root bridge designated port, right? So then the ports opposite it will be root port. So here you can see a root port, root port. Okay. Then the receiving port on the switch will be designated port. Okay, receiving to forward to the root bridge, designated port. Okay. Now we already know only one designated port per link. So by right, if this is designated port, this will be root port. Designated port, root port. Okay, but we will need to do a how to say election. Okay, because if we just put as a root port all then there is no blocking. We want the blocking, right? So we have a situation like this. S2 has two ports, F1 and F2, with equal cost path. Okay, 19 here, 19 here, pas internet kan? 19 here, 19 here. So they are all equal. So this way and this way, same cost 38, right? So the bridge ID of the S3 and S4 will be used to break the tie. Okay, it's known as sender's ID. Okay, remember just now we talked about the sender's ID, right? So in order to break the tie, we look at the sender's ID. So S3 BID and S4 BID. S4 has a lower BID. You can check. It's 5555 here, although the head part is the same, but the tail part S3 has 555555 and S4 has 11111. Right? So S4 has a BID of lower. Okay, lower BID. So due to that part, this is S4 is a sender for S2. S3 is sender for S2. So S3 and S4 competes. That's why we check S3 BID, S4 BID. S4 wins, right? So this port, right, that's connected to the switch 4, the winning switch becomes the root port. Then the other port becomes alternate port. All right? Is that okay?
Okay. Oh, is it only the root bridge can have more than 2 designated ports?
The root bridge is,
Oh,
the root bridge cannot have a, all right. So root bridge cannot have a root port because it's already root bridge. The root port is the one that's leading towards, okay?
yeah,
Traffic going out from it is leading towards the root bridge.
I just
Yeah.
asked if the other switch can have 2 designated ports.
Uh, hang on, probably not though. They can have a different path lah. That means you're talking about another alternate path, right?
Yeah.
Let's say I have here
There's like a third switch, and then they link
like
to the
this,
other two.
connect like this lah, like this. Is it?
Yeah.
Connect like this. So this, if I close this one, this is still a loop. So at the end, we still need to close the loop.
Oh,
Right? So this is still moving towards root bridge. So this is root port. So this will be designated. Right? Okay. So this is root port also. This is designated. Tapi this one kan, election between, now this election is between S2 and this should be, let's say this is S5. Right? S5. So election will be this and this to determine whether this, sorry, either this or this one is blocked. So it's like that. Yeah, this one. Oh, sorry. Or this one. Blocked.
oh, okay.
So if you just extend the same method will be done on that part, that alternate path. Right? So you cannot only block this path. If you have an alternate path, that one also have to be blocked. So that part, the other path will also need to go through the same process that we've done for this example.
Okay.
Yeah. So in answer, I think you cannot have more. If you're not the root bridge, you cannot have more than. Depends lah. I think if you have a different, maybe like this, still is it still gonna be if you block here. If you block here, it still can forward in a loop. No, it's direct. Become direct. So it actually depends on the topology. If I just add another switch here, okay, see whether there's need to be blocked. Does it form a loop? Hang on. Does it form a loop? Yes, it form a loop. So if this is root, this is designated, and then you have to check this or this. Yeah, still same. I don't think you can have more than one, no, because the link is still there. If I form another link like this, also still the same. I cannot see how you can have more than one designated.
Okay.
Probably lah, if like this. You see, this link directly bypass that one, go to here, right? Then depending on the election, this one already designated. This one can be designated, and then here root is designated. It cannot be designated to designated. So if I directly link to here, it's like connecting directly. Oh yeah, one of it must be blocked, right? It still must be blocked. Yeah. If I just connect directly like from that switch to this switch, then this is root designated. Probably this one will still be blocked. Yeah. Yeah. So far, I cannot see the topology. Maybe you can play around with your packet tracer and try to create a topology where you can see whether there's two designated port.
Probably cannot get two designated port.
Yeah, I'm trying to figure out how to how to design a network with where you can have two designated port. Because designated port is just open port, right? Which is not root port, right? So there are three types of port: root port, designated, and block. So if you root port always leading towards the root bridge, right? And the designated port is always receiving traffic so that it can forward to the root bridge. But sometimes, oh no, sorry, not sometimes, because of the STP, um, whether it retains as designated or it becomes alternate port, it depends on the election. The election where we actually look at the BID, okay, and we use this. I'm sorry, where we use this one. Look at what BID sender priority. If still tied, look at the sender priority. If still tied, we look at the lower sender port ID. We need to do the election. If this is not there, then the election is between this and this. Correct?
Yeah.
Can? Which one win? This one or this one? Again, we look at the BID no? Between this and this. Right? If there's not there, that means this is directly connected like this. Because it still form a loop, we still need to apply, the STP will still apply here. So let's say we don't have this in our topology. Even if we have this link, these two still need to specify which one is designated, which one is alternate port. Right? Okay. So there will be a situation like this, and in fact, next week we'll look at one kind of situation where we have more than one link between two switches. Right? We introduce this one to you without that knowledge in the next week because that's a separate issue, separate information. But I just give you heads up. Normally in a LAN, if you're wondering why we want to cable switches like this, in a LAN, especially with Cisco, Cisco allow you to connect in this way, okay? Two connection between the switch, okay? So when we have two connection like this, Cisco switch is able to, once you configure it, is able to aggregate the two links, mean they combine together to share the load. So instead of having 100 megabits per second per link, now it logically becomes one link, which is 200 megabits per second. Okay, so logically, it's as if the two links is one link, one 200 megabits per second link. Is another way without upgrading your switch to have a faster bandwidth between the switches. Okay, and we will look at it in more detail in next week Ether-channel, right? So that's why we can have this kind of topology lah. If you're wondering why do we have two links between two switches like this? Does it make sense? Yes, it makes sense. In next week we'll see why it makes sense. But we are given this topology, right? So can you see that if ether channel is not applied here, I mean ether channel is the aggregation of the two links. that this can cause a loop. Do you agree?
Will it cause loop?
Yeah. Can this kind of way of linking the two switches can it cause a loop? You know, the loop that can cause us problem where the frames can go around and round. Would this kind of
I think can.
can
I
that?
think, yeah, I think it
Uh,
can cause a loops.
Mm. Yeah. Thank you, Farah. It does cause a loop because when it enters, let's say the data from here enters here, it's being switched. It can go here. It enters here, it can be switched and goes here, and so on and so on and so on and so on. Same problems we encounter with the more elaborate topology, right? The more elaborate, what I mean is like, let's say we have something like this, right? We have done something like this. It goes round and round because we have this kind of topology, right? But this is actually very similar to that. It's just that it's simplified because the switch we're going to do the switching here. Then the two switches can allow frames to be switched to move around in the circle like that, similar to a circle like this, right? Okay, so this kind of link, if it's not ether channel, can cause a loop problem, right? So let's look at this example, yeah, for STP. Right, so elect a root port from multiple equal cost paths. So here, here is 19 is 19 because it's fast Ethernet, right? Both are fast Ethernet links. So the path cost is 19 here and here as well. So you are given the port priority is the same, port priority. Recall, I just go bring you back all the way here, right? BID, if it's tied, check port priority. If it's tied, check port ID, right? So port priority is given here, yeah. But unfortunately, it's not the same. But even though the same, we can check the bridge ID first, right? So the bridge ID definitely not the same. So this from the bridge ID we can break the tie, right? We already don't need to check the port priority. Okay, so this topology has two switches, S1 and S2. They're connected with equal cost path, both 19, both 19. Okay. S1 is the root bridge. So this one root bridge. So both of ports are designated, correct? Because root bridge, all ports will be designated, right? So if this is designated, this one will be root. This one will be root, right? But then here it can form. So one of the port F6 and F5 on S4 needs to be alternate port, needs to be blocked, right? Okay, so S4 has two ports of equal because the ports are connected to the same switch. The sender BID S1 is equal. So the first step is a tie. So both are in the same switch, same BID S1. So the first step is a tie, right? So here is 19. Here's 19. That's tied. We're not checking this. We're checking this because the port is on the same switch. So again, if we're checking that only, then of course both uh, both port has same BID, so that's tied. So next is sender S1 port priority. The default port priority is 128. So that's tied, right? Now it says here, however, if either port on S1 was configured lower port priority, right? So if anyone will be a lower port priority, winning lah. If this is lower port, then the adjacent port will be forwarding, then this one will be blocked, right? So if this one lower port priority, then this one will be forwarding, this one will be blocked. That's what it says. If any one of these port on S1 configured with lower port priority, lower, let's say this lower, then S4 will put its adjacent port. Adjacent port is here for the lower, since it's linked. Adjacent will be forwarding, means not blocked. Then the other port will be blocked, right? So if this is the winning port, lower priority, then this forwarding, this is blocked. Does that make sense?
They still get the same. They still get the same double the internet, double the G.
Double. Oh, you mean the link?
Yeah, the link still perform much better even like this. Even they have
Oh
still more
no,
of them blocked.
no longer, because then if this is blocked, then this link cannot use. It's blocked. Yeah, right.
So
Now,
all of them must be blocked to prevent the loop.
yeah,
So this way is still not good. So not a good, not plausible way to do.
yes. The only difference is if you're using something called ether channel, which is the topic of the next chapter, these two links will be seen as a single logical link. Since it's a single logical link, therefore no looping will happen. You can only loop within a two links, right? Two links means I can loop from here to here to here like that, kan? But for ether channel, the whole thing become one logical link. The software don't see the link as two links anymore. Okay, it's using ether channel technology. The two links become one link, so there's no need to do STP for ether channel. Get it? Is it okay?
Yeah. Okay.
Yeah. But we are not talking about ether channel yet. That's the topic for next week. But I just tell you first. Okay. Now here in this configuration, since we are not using ether channel, these two links are seen as two links, right? So one of them need to be blocked. Okay. So it's just that means this is just become something like redundant link lah. If one of the link go down, the other link takes over. Okay, because it's not configured as ether channel, so this is seen as two links. So two links, okay, connecting the two switches means the two links can form a loop. That's why we need to block one of it. Okay, we need to block one of it. So that's why we see just now. We try to compare. Let's say this is the root bridge. You have designated port, so root bridge will never get blocked, right? Okay, so that's why we consider on S4, because designated port is always the port on the root bridge, which is always open. Okay, so which port to close on S4, because they're both potentially root port. Remember, the opposite of designated port on the link is the root port, but one of them is root, one of them is alternate. So which one is first? We cannot compare the root BID, the root bridge BID, because both ports on the same switch, so they have the same bridge ID. So okay, that one is a tie. Move on, right? So we are supposed to look at the port priority. They are the same. In fact, if they're the same, we look at port ID. Okay, but the statement here in the slide say if one of the port here has lower port priority, okay, let's say this lower, then the adjacent one is a forwarding being designated lah. If this is the other one becomes block. So if this wins, the other port block. If this wins, the other port block. Okay, that's what it means lah. Right. Okay. So because our port priority is a tie, we need to break the tie somehow. The next one is the port ID, right? So do they give us port ID here? Still none, no. Right. So okay, so let's have a look first. The last tiebreaker is the lowest sender port ID, right? So switch S4 is the sender into the root bridge, right? Switch S4 has received BBDU from port F1, right? And port F2, right? Yeah, okay. The decision is based on the sender's port ID, not the receiver port ID, because the port ID of F1 on S1 is lower than port F2 on the port F6 on. Yeah, but how do I know the port ID? Again, it's not given. This is for me. I was trying to look for the port ID. It says it's lower. Maybe it just say given as lower. They don't give the information in this diagram, right? So maybe it's just in the statement itself, right? It's just basically tell us that F1 on S1 has lower port, okay, lower port ID. So definitely say that this is win lah, this win, because it's lower port ID. Okay. I was thinking of situation where they don't tell you that, so they must give you the port ID for the port so that you can compare. But it's, in this case, we are not given the port ID, but the statement is given, right? It says here, especially say here, the port ID of F1 on switch 1 is lower than port F2. So that means we know already the port F1 is the winning port lah, right? Because we want to look for lower port ID, right? All right, so because the port ID of F1 and S1 is lower than F2, the port F6 is the root port, right? So this port becomes blocked. All right, so it's given lah. It's given that the port ID for F1 is lower. Okay, and we have to go down to that as the tiebreaker because this one is equal, this one is equal. Then we have to go for port ID, and it's given that port ID F1 is the winning port, lower port ID. Again, you can see if you set that as the winning one, then the other one is the block port, because this one becomes the root port. Okay, is that okay? I imagine if you're given a test where this is equal, this is equal, you definitely either given the port ID to compare, or the question gives you which port is lower port ID. All right, they will not give you the port ID, and then if all equal. All right, if you discover that, highlight it. Highlight it. I think they wouldn't but just in case then you can highlight that part. Then we can question the the PIC, the person in charge. All right. Okay. So this one is okay.
This one, you check the port priority first and then the bridge ID, or the bridge ID first?
The bridge ID first.
Okay.
Bridge ID first, but this one, in this, in any other topology, I think bridge ID, you can differentiate already, but because of we are using the same switch, the same port, I mean the two ports on the same switch will have the same bridge ID. That is why we have to ignore the bridge ID because they are tied. Yeah, bridge ID first, right? And then port priority, and then port ID.
Okay.
Okay. All right. Ferro and all. Okay.
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 Okay. Right. So settling down. What I mean about settling down is actually that I was looking for that keyword. The keyword is convergence. Remember that in order for them to do all this election, they need the BPDU, right? The BPDU is shared by all switches in the LAN amongst each other, right? And the information from the BPDU is the one that they use to do all the information. For example, the BID, the priority, the what is inside there. Okay, and they need this information to do the election for all those root bridge, root port, designated port, and therefore non-designated port or alternate block port, right? So because it takes time for the BPDU to flow in the network and for them to retrieve and then for them to check. So there's a slight delay, okay, until from when the switch start operating, and once they're settling the order converge. We call it converge. Converge means all switches got all the information and they all did the election, so everything is settled, done already, right? That's conversion, right? So three step: root bridge election, root port determination on all the other non-root bridge, mean the non-root switch. Okay, and then once you get the root port, you can then decide which that means we can decide the designated port, right? And then another election, okay, on the BID, right? BID of the sender's switch or sender bridge, and then that will indicate to us which port becomes the block port, right? So in total, you have 5 decision to do as a switch when you're doing the election. Lowest BID. This one is used for root bridge election, and then lowest root path cost, right? And then lowest sender BID, lowest sender port priority, port ID. It says here the best path to the root bridge. Okay, yes, of course, the best path. Sometimes the best path for me, for us is this one. But what happens if you have equal, right? Then when you if equal, then you have to check this, check this, check this. So these 3 is used for to check the alternate. Remember, we use the sender BID, sender port ID, and port ID to figure out which one is the alternate or block port. Okay. All right. All right. STP time is excuse me. Yeah, I just need to go get some water first. My throat is a bit itchy. Pause for a couple of minutes. Is it okay?
Okay.
Okay.
Drink a glass of water. You guys can go get some water also. Right. Hello. Welcome back. Alright. Uh, got a much needed drink of water. Okay, so let's continue. Right. So okay, STP timers and port states. So we look at STP timers first. Right. So this is the timing required because you cannot flood the network with the BPDUs also, right? So how do you know when to send, right? Or how do you know? Because working on layer two, I think layer two do not have um, the transport layer. You know, switch doesn't reach. Not supposed to reach transport layer, so there's no how do you say this? Acknowledgement, lah, right? Okay, so you cannot flood the network. Therefore, you need to have a delay between when you send out and then maybe pause for a while, right? And then send out again BPDUs, right? Because you don't know whether the other switches actually receive or not. There's no acknowledgement in the layer two. So we have this something called hello timer, right? This is the time interval between BPDUs. When the switch send out the BPDUs, okay, then wait for a while until the hello timer, the time elapses, right? So the default for the time period between that means the intervals between sending out BPDUs is 2 seconds as the default, but it can be modified. So that means it's can be changed by the system administrator, right? Or network administrator, right? So the reason being we don't want the switch to be flooding the network with BPDUs. We know it's needed for STP, but we don't want it to be such that it's sent out that it actually detrimental to the bandwidth in our network, in our LAN, right? And then we have the forward delay timer. Forward delay is the time that is spent in listening and learning state. Means you as a switch, you're listening. Listening means simply you're open to receiving BPDUs. Okay, right. Also include the learning state. Learning state is when you listen, you receive, then you process. Right. So the default is between it's 15 seconds, but you can again modify that to a range between 4 to 30 seconds, right? Right. So maybe 15 seconds for us is that's quite a short time, but in terms of network forwarding, network flowing through the network, 15 seconds is quite a long time actually, right? Since the speed that we send is we're using electrical signal, so we actually measured like for example 100 megabits per second. So in 1 second, 100 megabits of data have been sent, right? So 15 seconds, quite a good time, right? To to uh, provide the delay between listening and learning state. Okay, so the third timer is maximum edge timer. This is the maximum length of time the switch waits before trying to change the STP topology. STP topology can change uh, when you change the topology of your network. This is because STP is automatic, right? So it works without you prompting the switch to perform the STP convergence. Therefore, there must be a way for the switches to auto check whether there's a change in the topology. Topology change basically means you unplug switch, you connect your switches differently, you add another switch and you connect it again. So that will change the topology. Changing the topology means the previous configuration for STP may not work anymore. So you have to redo your convergence, right? So since this STP is done automatically by the switch, right? So the reconvergence or reconfiguration of the STP must also be done automatically, lah. So we don't have, as a network administrator, we don't have to go and prompt the switch. Okay, now can you do the, check the topology again or converge again because, I changed the topology. No need because you have this max edge timer. The default is 20 seconds between every time to reconverge, but it can be modified. You can have a range between 6 to 40 seconds, right? The default times can be changed on the root bridge, right? And then from the root bridge it will propagate, okay? Propagate the new timer to the others via the BPDUs, okay? So that means that you don't have to go to every switch. Okay, you go to the root bridge, you change these values there, and it will be propagated to the rest of the switches. Okay, so these timers are just a way for us to sort of configure. If you take the default values, it's all right. So, okay, but it's a way for us to be able to configure the conversion times, the amount of um, the period between sending BPDUs and things like that. Okay. Right. So this is the figures earlier on shown in diagram format, right? So showing here that you have 5 states and 4 are operational port states. Okay. So disable state is non-operational, so that doesn't count lah. So the first state is blocking state. Okay, no BPD receive. Max age is 22nd. I think is this one. Right? Okay, listening, which the forward delay is 15 seconds, right? And then learning is forward delay after listening 15 seconds, learning 15 seconds, and forwarding. And then we have the blocking state. In blocking state, until STP determines port is root or designated port. That means it will not, while it's electing, it will not forward, right? So after link turns green on your packet tracer, or even on your machine, the links become green because you plug in, right, the cable. Then it goes into blocking until all the election for ports, root or designated port is done, right? Okay, and this is the listening part lah. Okay, while the listening part, when it will get all the BPDU, right, and then it will use the BPDU in this part, learning part. This is the conversion part lah. To basically, the learning part here is to determine port is root or designated. This one lah. But this is while this STP is determined, okay, ports will be in blocking mode even though the link already comes up because it's learning. It wants to immediately stop if there is any circular, right? We all want to prevent that. Okay, so the listening, this one is listening for BPDU. Okay, and then once it learns already, that means it's converge, then you start forwarding, and that is what the switch does lah, forwards frames, right? So once the learning process done, everything converge, identified all the ports or routes or designated or block ports, then it'll start forwarding already. So same thing in table form. You can see blocking, listening, learning, forwarding. Disable, again, disable. Okay, state is not considered operational. Okay. right? Okay, so VLAN, just now we consider spanning tree. The previous week, we considered VLAN, virtual LAN. Okay, this week, we move on from VLAN, right? We just considered spanning tree in terms of single LAN or single VLAN. Okay, by default, it's VLAN 1, isn't it? By default, if we don't create any other VLAN, by default, everything is on the switch is VLAN 1. So the spanning tree we done so far is based on VLAN 1, right? So the thing is, um, you imagine with creating virtual LAN, and the virtual LAN, the way you configure, okay, this switch will forward VLAN what. This computer belongs to which VLAN. Okay, depending on how you configure your topology for your virtual LAN might be different from your topology in the physical LAN. You get what I mean? If you have a more complex network, you have many switches. Okay, maybe two switches will propagate forward VLAN 1 and 2. Maybe another two switch will propagate VLAN 3 and 4, or something like a combination. Just so far we learned, okay, we have two switch. We use trunking to convey all VLAN data. Correct? Calvin, Ferrer, Noel?
Mm,
Yeah? You understand? Yeah? Like what I say is, so far when we consider virtual LANs, when we have multiple VLANs, right? We always consider the trunk link to carry all the VLANs data. We just tag it with VLAN 1, 2, 3, or not VLAN 1, VLAN 10, 20, 30, 40, whatever, right? But imagine if you have a more mesh kind of network. Your switch. So this switch will, and this switch, the links, they just carry this set of VLANs. Another two, three switches carry this set of VLANs. You know, you can configure that way, right? Can you imagine that? Not
oh,
necessarily.
yes.
Yeah, you can consider. Not every switches must carry all the VLAN traffic. Again, I say depending on the configuration, you as the network administrator, how you want to do it, right? So, which means when you look at the physical LAN, you can see the topology. But when you look at virtual LANs, because you have many virtual LANs, you configure it differently. This switch only transfer this switch convert this. Then your topology for virtual LANs maybe not the same as your physical LAN, right? So some of the virtual LANs, perhaps, if you consider virtual LANs now, can create loops. Even though your that means because you have more than one virtual LAN. Okay, by default, virtual LAN is only one with VLAN 1. When you start create VLAN 2, 10, 10, 20, 30, or something like that, right? Okay. Now you have to consider not only the physical LAN, now you have to consider each virtual LAN. Because depending on how you configure the virtual LAN, right? Of course, the physical LAN will affect it also, because the virtual LAN can reflect on what is the physical LAN, physical topology. But now because you're doing multiple virtual LANs, and maybe your configuration, thereby your topology for each virtual LAN will be slightly different. Now you have to look at your virtual LAN topology, okay? And you might notice that, hey, hang on, this virtual LAN 10 topology can create a loop, right? So then you have to create STP or enable STP for that virtual LAN. Or you might end up enabling STP for all virtual LAN, right? So you can see this is what it means here, right? STP can be configured to operate with multiple VLANs, right? So when you have multiple VLANs, you have multiple spanning tree, which is means it's called per VLAN spanning tree, PVST. So that means in each spanning tree there must be a root bridge. Okay. So unfortunately, if you're multiple VLAN, if your VLAN all have different topology, because the way you configure it on your physical topology, then you have to check each each topology they need or not. Okay, they need STP. Maybe they need, and then you'll notice that for a PVST configured or converge on per VLAN spanning tree, there will be they will each have a root bridge and so forth, like what we created for single network just now, right? So it makes it possible to have different root bridges, different VLANs. So each STP will operate for each VLANs, right? Okay, the example,
Okay.
yeah, the example we did just now was assumed to be by default VLAN 1, right? So all for VLAN 1. So if you remain on one VLAN, which is VLAN 1, which is the default, okay, then you only have one spanning tree. But if you have multiple VLANs, from last week, we create VLAN 10, 20, 30, something like that. So each of those VLAN will have their own spanning tree called PVST. Okay, so that means the switch
Okay.
is quite capable to have instances of this spanning tree. Yeah. All right. So we want to end with this evolution, mean how it progress. Okay. How is the progression of STP, right? So just now of course we focus on the Cisco version of the STP, but there are various implementation. So some of them with their own name. You can see here Rscp, Rapid Spanning Tree Protocol, MSTP, Multiple Spanning Tree Protocol, right? So because of these variations, there's various implementation of spanning tree, right? And we try to think about spanning tree in terms of standard or implemented. So there is and the body that basically look after our local area network. Okay, all the standards within the local area network usually is from IEEE. So IEEE do have documentation on spanning tree. They try to provide standard, and you can see there on the screen is IEEE 02 1B 2004, right? So it says there STP has been superseded, means STP, the earlier version is now superseded. Superseded simply means there's a new version called Rapid Spanning Tree Protocol, right? So IEEE, in order to not confuse practitioners or the industry, when they use the terminology STP, that terminology refers to the original implementation. I shared the document already. That research paper. That research paper is, I think, one of the example of a very good um, ideas lah. Because the idea from that research paper was is now implemented in all networks around the world, local area networks or a spanning tree. Very important lah. The idea behind it, the spanning tree. Right. So if you want to refer to the version that is specified by IEEE, you need to use the terminology Rstp, right? But when you look at these two protocols, they use the same terminology within their implementation. It means the same keywords, and the methods for basically the steps that we go through earlier on is basically very similar. Okay, so for Cisco Cisco focus on the current standard and their own proprietary implementations, right? So remember the PVST, that is the per VLAN spanning tree. So because Cisco switches support VLAN, so Cisco has to amend the spanning tree um, running on their switches to be able to cater for virtual LANs. And they call their implementation the PVST plus, per VLAN spanning tree, right? So Cisco version, you can see there, it says it still follow a lot of the original specification for the Rscp. Okay, when you refer to IEEE documents, it means we have to use the keyword Rstp to indicate, right? So the terminology like alternate ports, okay, used to be called non-designated port. Makes sense now, right? Designated, non-designated port. But I think IEEE, they want to improve the clarity. So instead of just saying non-designated port, because non-designated port are the ports that's going to be blocked anyway, right? They just call it alternate ports to differentiate lah, to make it. Sometimes the wording is very carefully placed in documents so that it becomes clearer, gives more clarity, concise lah, right? So in terms of, and this is very important lah, especially if you want to be precise, because your document will be used to implement because it's a standard, it might be implemented. So if I'm a manufacturer for switches, okay, I need to understand your document accurately, so that I don't make mistake when I actually do implement your protocol in my switch, for example. That's why it's very important, the terminology. So the older Stp and the more recent IEEE version and Cisco version, because Cisco basically follow the IEEE, so the terminology the same, but sometimes still revert back. I notice also sometimes they still put non-designated ports, but actually if you follow IEEE, should be alternate ports, right? So switches must be explicitly configured for rapid spanning tree mode in order to run the Rscp, which is what is indicated in the IEEE document, right? And this basically refers to Cisco. Right, so this diagram of table shows you the different versions now, right? Okay, so you have a read through. For us in this chapter, is more important to understand how the why and the how the spanning tree protocol or algorithm works. Okay, so this one is just this extra information for you to provide context on the STP implementation, right? Okay, so the different version. So you might be wondering, so hey, how come it's called Rstp and STP? And okay, so these are the description, brief description to show you the difference of the implementation. But at the heart of the implementation, right? The idea is still there, the from the STA, from the original algorithm, right? So whether they have many version or not, okay, for our purpose, for this course, the explanation provided, that is the way that the current current single VLAN configuration works for the Cisco switch, right? Right. So it's still this one still talk about the implementation of it, right? So you can see here we talk about Rscp, right? Rscp increase the speed of pre-calculation. Remember, there's a delay. It's aging timer. whereby no changes to the topology is entertained until the timer elapsed. Then they start learning again, start learning again, receiving BPDU, and then try to converge again. Yeah. So that convergence is actually a recalculation, the election that's happening. So obviously, any latency in that also affect the latency of the forwarding in our network. So the faster you do that recalculation, the better it is. So that's why we always try to improve the election process or whatever the process is. So you can see that the Rscp basically increase the speed of the recalculation, right? Let's see. Right, so let's move on. Okay, so now we're going to look at the Rsdp port states and port roles. Okay, so there are 3 port states in Rsdp compared to the Stp, right? With the IEEE standard, disable, blocking, and listening state are merged. Okay, are merged into something called discarding state. So the original STP compared to the Rsdp that is currently used, disable, blocking, and listening we learned about earlier on is basically, I think, combined lah, right? Combined, the functionalities combined to form a new state called discarding, right? So root ports and designated ports are the same in both implementation, STP and Rsdp. Okay, so the block port, the non-designated port now has two different terminology, right? So they further broken down the block port into 2 ports called backup port and alternate port, and it's shown here lah, right? So you can see alternate port, backup port, right? The alternate port is an alternate port to the root bridge, what we did earlier. Backup port is a backup to a shared medium such as a hub, right? Okay. So, but the thing is, backup port we can consider or not consider because backup port is basically to a hub. A hub is a legacy because not many people seriously want to configure network with a hub. Hub is a shared network. Remember the collision domain earlier on, right? Switch reduce collision domain. Hub actually increase the collision domain because hub is shared and is also very prone to collision because hub is half duplex communication, right? So half duplex communication, shared network means potential for collision is there, right? So it means slow. Okay, to normal everyday people, that means slow network, right? And so we don't really consider that anymore. But if you do have a network that still have this hub, and sometimes it's a mixture of legacy and new network as you slowly get the budget to, to improve your network, right? So if you still have hub, then that you can see here, there's a potential to have a look there. So of course we block one, so we call that backup port. Okay, the one that's leading to hub. Okay, if the normal switch, modern switch, we call it alternate port instead of backup port. Okay. Right. So I want to talk about port fast and BPDU guard. Right. So think about when a device is connected to a switch port. For example, your PC0 here, right, is switch on. You switch on, so it starts to connect to your switch, right? The switch port will go through listening learning states, each time waiting for forward delay timer to expire. This, and this refers to the previous that we look at the what the switch go through. Do you recall that? This one, this state, the switch goes through this state. Remember, guys?
Oh,
Yeah, remember this? So we're looking at that here. Oh, sorry, not here. This one. Okay. Switch goes, port goes through this each time, waiting for the forward delay timer to expire, and it keeps on going because it's automated. Okay, and also there's that learning and also converging to a new, just in case the topology change. Right. So this delay is 15 seconds for each state for a total of 30 seconds. Right. And the problem here is when a device or end device just connect to the network because you switch on the computer, for example, or you plug in, then if your device is set to DHCP, that means you didn't put static IP, and it's normal. Sometimes you want to put static IP, sometimes you want to put DHCP to your device, right? So if your device is on DHCP, the first thing your computer will do is the network stack is to get to try to get the IP address for your device. So it will start to search for DHCP server and it start to request, you know, the DORA thing, the discover, offer, request, acknowledge for the DHCP. Yeah, so that your machine can get the given the IP address, list out the IP address from the DHCP server. The thing is, because of the delay happening with the switch, the moment you connect to a switch port, it detects the switch port got something connection, I got some signal there, is to do the thing. This one, the state, it goes through the state early on. So 30 seconds is quite slow, too long, and the DHCP process might be timing out, detecting it cannot reach the DHCP server. So when it doesn't receive any DHCP reply within 30 minutes, 30 seconds, it will complain. It will complain. It will give up. Therefore, your computer cannot get an IP address, right? Okay, because remember, during this state here means blocking. Okay, there is no forwarding. You can see the table just now, the table about the state and the state of the switch, whether blocking or forwarding when it's doing all this STP, right? What's the cure? We don't want that, right? So we have something called port fast. If we configure the switch port that's connected to your end device with port fast, the port transition directly from blocking to forwarding means it's keep all the states early on. Makes sense because you're not a switch. Correct? You're not a switch. So there is no need for you to go through. You're not a switch, that means you cannot affect the topology. Is that correct? Kelvin, Farah, and Noel?
yeah.
Yeah? You're an end device, right? You're detected to connect to the switch. But can an end device change the topology? Requiring STP. So I know you're a bit soft, huh? I can't hear.
I think any device can change the topology, right?
Can it change the topology?
Right? Or is it only the starting?
Okay, the topology change that we are referring to is this type, where it can create loops. So does it make sense that only the switch a switch you add into the topology or remove from the topology will change the topology. If I add PC or end device, does it change it?
Oh, and doesn't change much. Yeah.
Not really, can?
Yeah.
So since whenever you plug into the switch or it detects a current because you switch on your PC, the link light start coming up. It goes through all those. You want to detect. It detect. Oh, this switch become active. Okay, it cannot differentiate yet whether it's a switch or it's a PC, or it's just know that something connect to its port. There's activity lah. So it goes to those state, listening, and trying to converge. But we know, okay, hang on, this is PC, so it's not a switch, so it's not going to change the topology. So maybe we can bypass that, skip that part, right? Don't need to do that. Why? We want to make it fast because we don't want our DHCP or any other services timeout because of the blocking, right? So we have something called port fast that we can configure on the port straight, right? Which means if you configure port fast on that port, it's straightaway transition from blocking to forwarding, and it avoids the 30-second delay, right? So that's why if you designate a port on the switch that is meant to connect to host, configure that port to be port fast so that it bypass all this delay for converging STP calculation, right? Because there's no need, because this is a device, it's not a switch, it's an end device, right? So port fast. Okay, so port fast, please don't use port fast on this because if you use port fast on those kind of ports, because they're supposed to be designated or root port or block port, and you will disrupt the STP calculation, or yeah, it doesn't work anymore if you do that, because it bypass all the listening, the converging, right? So when you do that, then you encounter this spanning tree loop. Okay, right. Now another thing, the port that leads to end devices, okay, is enabled with port fast, right? So that it skips all those things that cause delay, and it also should not reach BPDUs. I mean, receive BPDUs. Okay, those ports should not receive because they're not supposed to receive, because they are not connected. They're not connected to any switch. They're connected to PC, right? So in we have this BPDU guard, because if you enable this switch to receive BPDUs, then again it thinks that it's connected to another switch. So what we want to do is block, not only put it port fast, we block the receipt of BPDU on that switch, the port, switch port that leads to the end devices. All right. Okay.
Okay.
All right. So those are the two, port fast and BPDU. This affects ports on the switch that is linked to end devices. All right. So alternative to STP, I think again, the discussion is on Rscp, okay, and MSTP, right? So there's not much as algorithm change. STP is based on STA. STA, I think it's worked well so far, right? And they keep improving it. They keep improving the algorithm in the sense that they keep finding ways for faster conversion, faster calculation involving the election of root bridge and things like that, root port and there's another port, right? So still not much changes to me lah, in terms of algorithm wise. STP is still there. It's just that they improve or add certain things to improve just a little bit of it. That's why we have those Rsdp and MSTP, right? But we cannot deny that compared to layer 3, STP is an add-on. It's something that is put there to fix a problem, right? Whereas in the layer 3, there's no problem because the solution is part of the protocol itself. Remember, TTL is built in. It's a field inside there, and the intermediate device, the router, simply deduct. There's no conversion, there's no learning, there's no PDU and all these things. So it's more efficient. The way they deal with the loop in layer 3 is better, right? So you can see there. And yeah, one thing, they don't have to block ports because they don't allow packets to travel forever. Based on the TTL, packets can be dropped if it keep on traveling, right? So later it will be dropped. So no block ports is good. There's no learning period. There's no all this whatever. Okay, in layer 2, right? So some environments are transitioning to layer 3 everywhere except where device connect to access layer switch. So you start to see why, if possible, I think a Cisco is looking at layer 2. Layer 2, I will find the article. Last time I have the article already. It details the story of networking from the beginning. It's not dry, it's not boring, but it tells you why certain things in network is the way they are and what is the problem and why it's so hard to get rid of the problem. The thing is, we can see here, there's a hint here, right? For this reason, some environments are transitioning to layer 3 everywhere except where device connect to access layer switch. In other words, the connection between access layer switches and distribution switches will be layer 3 instead of layer 2. As much as possible, they don't want to deal with layer 2 because layer 2, a lot of things it's a tech-on solution. It's a MacGyver type of solution. You guys know MacGyver or not?
No, I think
MacGyver? No.
MacGyver is like in a American TV series.
Oh, the one that can open doors, lock, and all, right?
Yeah, he always do. He has no probably he has no tools, no nothing to it, but he can always use the whatever tools to fashion whatever solution to whatever problem right there and then. Yeah, it's quite cool to see, but that is not good actually. Means lack of proper planning and right? So that's why I say this. A lot of the solution to solve certain problems in networking is kind of patchy, kind of MacGyver style. Okay, we have this problem. Can we have a solution? Then they find out something. Like, oh, okay, this one fix it. Yeah, all this. Remember, you guys have to do all the segmentation of the network. In your first course, you have to learn how to do the network segmenter, right? You divide the network into first of all, it was classful. Then they feel that classful not good enough, do classless. And then after that, they want to do because classless. Then all this are just tech-on solution. So STP is actually a tech-on solution, and we're lucky that someone actually come up with a solution, right? But it's a solution which provide some problems lah. Okay, some problems, not really problems, but additional effort. Okay, but in layer 3 is basically it was designed to, but all the layers have problems lah. That's why I said I'll try to find that article that will explain, and it's a quite fascinating read, right? Okay, so please read this on your own. This was basically tell you what you have gone through this in this chapter. All right. Okay. So we finished the chapter. Do go for 10 minutes break, and then we have half hour to do the continue what we did yesterday. Yeah. Okay. So yeah, 10 minutes rest. You go for maybe toilet breaks, drink some water, and we come back in using our tutorial meet. Yeah. So I see you in the tutorial meet, and we proceed
Okay.
with the tutorial from yesterday. error for question 3. Okay, so the switch in question is switch W, right? So before you know which one is root port, you identify which switch is the root bridge. So based on the priority, you notice that switch Y has the lowest priority, 4097. So switch Y is the root bridge. Therefore, you're right, gig 12 and gig 11 are both candidate root port. Okay, so which one is the root port? Okay, if gig 11 is the root port, gig 12 become designated. If gig 12 is root port, gig 11 become designated. So you have to select which one. So based on the election, right, which one will win? So what kind of election? I let you find out yourself. Okay, which path win the election and what kind of election is that? That one I let you find out which one wins the election, then that one becomes the root port. So it's either gig 11 or gig 12. Right? So I'll let you try first, yeah?
Okay, I try first.
Ah. Noel, your answer correct. I'm marking it, but can you improve your answer, Noel, by specifying only the port? Sometimes it can be misleading. So can you also like port and the switch? That means port on which switch? Okay. For example, your answer for question 1, part 4, correct lah. Designated port on segment 1 is FA01, but which switch? So so that you get used to the answer. Also, actually, part 3 also you have to put in lah. Whenever you mention port, you have to qualify the port on which switch. Is that okay, Noel?
Okay.
Or else you don't get the full mark though on the test or exam.
So every time we ask for the port, have to specify the switch.
Yes, definitely.
Okay.
Yeah. Okay, so for Calvin, yeah, you're doing question 2 on part 2, root port on the non-root bridge. So your first answer is correct. Switch B on gig 01, but there is more than one non-root bridge.
Oh, all right.
Yeah. So can you add? Okay. Yeah, 2 more. I'll just tell you, just 2 more.
Yeah, one for each switch, right?
Yeah.
Oh,
Yeah. So switch B, C, and D. That's correct. But the switch C, the port
oh yeah,
is incorrect.
yeah,
For
yeah,
part 2.
yeah. I got it wrong. Switch C. The root should be. Okay. Oh, yeah. G1.
You correct part two first. Then you see, because you get the root port correct first, and then you get the switch. Sorry, the designated ports.
Oh yeah, I combined them.
Yeah, this one, the switch CG02 for part two, it's incorrect. You fix this one, switch
Oh.
C. Okay.
Hey, I didn't change it. Sorry.
So if this one have to check the port. So if since G01 is lower than G02, so we automatically choose G01.
Sorry, Noel, which one are you talking about?
This one question two.
Question.
to
Your
two.
question one.
This one. No, Kelvin.
Kelvin punya,
Question.
yeah.
Is it not G02 because it is short?
Okay. Right. So you identify the root. Which switch is that?
The root is
Switch
the
A.
switch A, and then
correct.
that's the designated, and then there's the root here.
Yeah.
Root here.
So the switch B root will be G01. Switch D root F024, and then switch C. When you want to indicate which root, which one is the winning, G01 or G0.
Oh yeah. Yeah.
You have to know which one is winning. Cannot be too.
But the Z02 take less, and
Yeah, I think the part two already correct.
So
So
the one we
check back your
look
part.
at.
Yeah.
We look at the port number for this case. For switch C.
the switch C, the port G01. Why Z01? Since Z01 travels the gigabit line and then need to go to the fast internet line, wouldn't that make it slow, make it not optimal to go?
Okay, so path in terms of path cost, 419, the same, right? G02 is 19 plus 4. G01 is 4 plus 19. So the same, right? So when the path cost is the same, then we check something else, right? So we check priority is the same. So if priority is
why the switch B, the FO2 is the fast is FO2 and then it linked to G02. Then how do you count that one?
again, what's your question? F02 on switch B. Why does it link to switch C?
Switch C G02, and then if like that, how we count as which we count as gigabit or fast Ethernet?
Yeah. You're right.
That one's I confused. Yeah.
I see. Yeah, you're right. I didn't notice that. I think there's a typo.
Oh, typo.
Yeah, sorry. Yeah, I think there's a typo. Cannot be F02. If you connect like that, F02, G02, you're right. It will drop down to the lowest speed, which is F02. So lowest speed, then 19 lowest speed lah kan?
Yeah.
So yes, correct lah. No error actually. Yeah, you can plug in fast Ethernet to gigabit Ethernet. It's just that you don't get the gigabit speed.
Oh, that one.
The speed will fall down to the lowest speed, which is fast Ethernet.
Before the
Then
lowest
it will
one.
be 19 lor.
Oh, okay.
Yeah.
That one, like that's the only part I confused.
Yeah. So Do you know why switch CG01 wins?
Oh, because the MAC address.
Yeah, correct. MAC address is lower for switch D.
Oh,
Yeah.
okay.
Designated port is F02, switch C. G0, switch D, designated port.
So remember, on the non-root bridge, your designated port is the receiving port, right? So if
Oh,
the receiving port towards the root bridge.
yeah, should be one every one of them just opposite each other. Okay. Uh, yeah. Hmm. Yeah. I guess I still struggle a bit at this one.
Yeah, it's okay. That's why I did the tutorial. So yeah, you continue first. I check Noel's answer first.
Okay.
Number 4, designated port on segment 1. Okay, that's correct. Designated port on segment 2, F42, yeah, correct. 6, non-designated port on segment 2 segment, F403 on switch B, correct. Port in blocking state. Noel, if you look at
Yeah.
the question 1, part 6,
Okay.
you put in as FO2 in switch A, right? You already identify non-designated port. So what is the non-designated port known as? Alternate port, right?
Hmm.
And what happens to
Oh,
alternate port?
it's block.
Blocked, yes. So that means the answer for part 6, the port is in a blocking state. You actually already have that answer in part 7. You already know the answer in part 6.
So is it FA01?
No, you see, you only have 3 types of ports, right? Root port, designated port, and non-designated port. Designated port, still forwarding. Means non-designated port is the one that is non-forwarding. The other name for non-designated port is alternate port. And what happens to alternate port is that it is blocked. So the question part 7 say which port is in blocking state, which means the block port, right? Which means alternate port, which means non-designated port.
Oh,
Yeah.
it,
Since you already gave the answer in part 6, then your answer for part 7 is actually
the same.
the answer from part 6. Okay.
Oh,
So non-designated ports are blocked. So all non-designated ports are in blocking state.
like this.
I think okay. Not sure. Should be okay. Each answer only 3 ports, right? Also can check the other answers here.